Welcome to part 4 of the Glacier Mass Balance lectures. My name is Andrew Mercer and I will be giving a brief introduction to the basic processes of glacier mass balance. So far we have looked at the glacier surface and its changing appearance. In part 4 we will take a brief look at how mass balance is measured. To begin with, I should mention the hydrological method. This method relies on measurements of precipitation and stream flow. It is the least common method, but it can give valuable data, especially for estimating internal processes. The two main methods of mass balance calculation are the glaciological method and the geodetic method. The glaciological method requires measurement each mass balance year and can be compared with accountancy. Sum the net gains and the net losses to obtain a balance for the year. The geodetic method measures the volume of the difference between the glacier surface at 1 year and a subsequent year. The geodetic method requires a topographic survey of the surface to be performed at intervals that guarantee the survey errors are not larger than the change being measured. Traditionally, aerial photographs have been the main source of data for generating elevation models, but these are quite problematic. The errors have meant that most surveys are separated by at least 10 years. Ground-based surveys, such as with a total station or survey quality GPS, require many hours in the field and can be dangerous. The accuracy of these surveys is usually much greater compared with aerial surveys, but the cost and risks limit their use. Recent developments in LiDAR and UAV technology suggest that frequent high-precision surveys will soon be available relatively cheaply. The basics of geodetic method are easy to grasp. The glacier surface is measured at the end of the ablation season in year 0. Then, at the end of a subsequent ablation period, the surface is measured again. The volume of the difference is converted to mass using the density values for ice, firn and snow. It is often here that the problems can arise. Without measurements of the distribution of density in the snow and firn zones, Sorge's law is applied, which assumes that the relative distribution is unchanged. The geodetic method can account for some internal accumulation and ablation that the glaciological method misses, but this too requires time for these to affect the dynamic adjustment of the surface, otherwise short-term density changes are unobserved. The glaciological method sums year by year the mass added in the accumulation area and the mass subtracted in the ablation area. We may start by measuring the accumulated snow. This, as mentioned previously, is done by probing snow depth and measuring snow density. We then measure the amount of snow and ice removed during the ablation. By measuring total accumulation and ablation, we can calculate the amount of water that the glacier contributes to stream flow. If we wish to simplify our measurements and only calculate the change to the glacier itself, then we need not measure the accumulation in winter, but only the amount of new snow left and ice removed by the end of the ablation season. From this we can see that the timing of the last ablation measurement at the end of the hydrological year is of central importance. By surveying on the last ablation day, we avoid calculating a positively skewed net balance. How this is determined is a rather vexing question, as the transition from net ablation to net accumulation is not a single event in time or space, but a rather gradual process. For this reason there exist differing methods for timing of the mass balance surveys. The stratigraphic method aims to measure the mass balance components precisely at the end of the season, adjusting to the prevailing conditions for that year. The fixed date method measures mass balance on the same date each year and then assumes that the errors are small, as air temperatures by this time are close to 0. We can also see that if we fail to capture the maximum accumulation at the end of winter, the net balance is unaffected by this, but the glacier's contribution to stream flow will be underestimated as a portion of the snow will accumulate and ablate without our knowledge. There are many variations on method, timing, coverage and interpolation, from single-stake surveys at the ELA to full coverage such as at Stockholm University. The problems of mass balance measurement are many, and though we can describe an idealized methodology, constraints of budget, weather, time, and safety mean that we must measure mass balance as appropriate. We will now briefly run through the stages of mass balance measurement as performed at Storglaciären. At the end of the winter, the snow depth is probed across the glacier in a grid 100 by 100 meters. This requires practice, especially in the accumulation area, where snow depths of several meters can make distinguishing the transition from snow to firn quite difficult. Snow density can be sampled using one of several methods. The pico drill is a corer that extracts a snow sample from the surface without the need to dig a pit. Whilst this is a useful tool in some circumstances, it is difficult to use. It is prone to errors and sample loss, as well as getting stuck. If anyone would like a pico drill head, there is one on Blåmannsisen in Norway. Alternatively, we can dig a snow pit and take fixed volume samples through the snow pack. This is a laborious and time-consuming process, but it works. A new method is to instead dig a pit, still laborious, but sample density using a snow fork, which measures the complex signal of the snow's conductivity. Come the ablation season, we must measure the ablation stakes, which were drilled at the end of the accumulation season. This seems on paper to be a simple task, but has proven to be quite problematic and requires teamwork and double-checking at all stages. Remember that because the ice flows, trying to maintain dynamic equilibrium, the elevation of the ice surface cannot be used as a measure of short-term volume change. Using stakes drilled into the ice before ablation starts, the amount of snow and ice lost can be measured. These stakes flow with the ice and are either buried by accumulation or melt out due to ablation. So for 2011, the snow density pits gave these results. The snow depth distribution looked like this. The ablation stake readings looked like this. And these gave the following interpolated maps of mass balance on Storglaciären for 2011. Accumulation, ablation, and net mass balance. We can also present the data in table form. At the top we have the equilibrium line altitude for 2011 at 1585 meters above sea level. The accumulation area ratio at 24.5%, i.e. 1/4 of the glacier's surface, showed net accumulation. Below this we have the mass balance components presented in 20-meter elevation bands, starting at 1140 to 1160 meters above sea level. The area of the glacier in this range, the volume of water accumulated in this range, accumulation in meters of water equivalent spread over this range, the volume of ablation, ablation in meters of water equivalent, net volume change, net meters of water equivalent. Then for each 20-meter band until the end into the head of the glacier. Finally, the sum of all these parts. So this is how the mass balance chart for Storglaciären is derived, with accumulation, ablation, and net balance summing to give us the change in Storglaciären's mass year by year.